Kia ora. Robert McLaughlin here. Welcome to week 10 of Differential Equations 1. This week we'll be looking at nonlinear systems of ordinary differential equations, having studied linear systems. Of course, they're going to be a little bit more difficult, therefore we can not say as much about them, but we will learn this week that there's a very close connection between linear systems and nonlinear systems. So all the stuff we learned about linear systems previously can be applied to nonlinear systems as well. Today we're going to start with the concept of stability. So we're going to consider a very large class of systems. So consider an arbitrary system of nonlinear ordinary differential equations. So x here is going to live in Rn, and n might be a large number, so this could be a large system of coupled nonlinear ordinary differential equations. And you want to imagine the case when you can't solve this differential equation analytically to get a formula for the solutions. So what can you do? Well, you can find the fixed points. So that is a point x hat, we'll call it, such that f of x hat is 0. So that means, if you can find such a point, that means x of t equals x hat for all t is a solution. They're the constant solutions. If you start at that point x hat, you will stay there forever. And you can find them by solving a system of algebraic equations, namely f of x equal to 0. The question about stability is, what happens if the initial condition is close to x hat? If you start close to the fixed point, will you stay nearby forever, or is it possible that you'll move far away? Now, we'll see when we write down the definition that we need to be a little bit careful about the precise definition of stability of a fixed point. Well, let's explain that through the definition. So here we are. And I'll draw a picture which will explain this rather slightly complicated definition. The definition says, a fixed point x hat is stable if for all big R there exists a number little r such that this is your distance from your solution to the fixed point always stays less than big R for all solutions that lie closer than little r. So let's draw a picture to explain this rather complicated definition. I'll draw it as if the system was in 2 dimensions. But of course it would apply in any dimension, and here will be the fixed point. I'll just imagine it's at the origin, but it could be anywhere. So there are 2 circles here. It's going to be a circle of radius little r and a circle of radius big R. And what the definition says, for any number big R, I can guarantee that I'll stay inside that circle forever, provided I start within the little circle. So that means that you may be able to start here inside the little circle. You are allowed to move away a little bit, as long as you stay inside the big circle forever. Of course, you may also turn out to stay inside the little circle and never move any further away from the fixed point than you started, but you are allowed to move away a little bit. And that's because it's quite possible, as we saw when we were doing linear systems, in the case of a center, you can have a solution that looks like this, a phase portrait that looks like this. This fixed point here is stable. So if I start here, close to the fixed point, I do move a little bit away. I can move maybe a factor of 2 or 3 away, but not arbitrarily far away. So a stable fixed point may look like this, or it may look like this. Where everything does just fall in. Or it may look like this. Everything spirals in. But it can't look like, so those ones are all stable, An unstable one may look like this, for example, the cell. This one is unstable. How does that work? To be stable, it would have to be the case that for all big R, so pick a big R, can I find a little r such that all initial conditions starting in the little circle would stay in the big circle forever? No, because I can always find, no matter how small I make that little circle, I can always find one point that will move outside the big circle. It does take a little while of thought and looking at the examples and going over this to understand this somewhat technical definition. That's called a stable fixed point. If this does not hold, then the fixed point is unstable. Now there's another stronger kind of stability which says a fixed point is asymptotically stable if it is a stable fixed point and if in addition all orbits that start in the little circle tend to the fixed point as t tends to infinity. So you could look like this, for example. Here's an orbit that starts nearby. It may move away a little bit, but it must tend to the fixed point, getting closer and closer to the fixed point, limiting on the fixed point as t tends to infinity. It could do that through a spiral or just going directly to the fixed point, but it must, all orbits that start nearby must tend to the fixed point to be asymptotically stable. So the big question is, I've got a nonlinear system. I've found the fixed points because that's relatively easy to do and there might be quite a number of them. Now you want to know, are those fixed points stable or unstable? And it turns out to be a more subtle question than you might think. For some fixed points, we will easily be able to determine whether they're stable or unstable, and for others it's more complicated and we won't be able to tell. These fixed points, they sort of form the organizing centers for the nonlinear, for the phase portrait of the nonlinear system. Okay, well let's try an easier case. Let's just try a one-dimensional system. So not a system of differential equations, just a scalar ordinary differential equation. And let's consider an example, the one that we've had already, say x prime is x minus x cubed. That is x 1 minus x squared. If I graph that right hand side, f of x, what does that look like? The graph of x minus x cubed looks like that. It has zeros at minus 1, 0, and 1. So if I draw the phase portrait, I can draw the fixed points, minus 1, 0, and 1. But I see if the initial condition lies between 0 and 1, f of x is positive, which means I move to the right. If the initial condition lies between minus 1 and 0, f of x is negative, that means dx dt is negative, that means I move to the left. And similarly, if the initial condition is bigger than 1, I move to the left. If the initial condition is less than minus 1, I move to the right. So now, if I combine this phase portrait that I've drawn with the definition of stability on the previous page, I see that this one is stable, and indeed it's asymptotically stable. This one is unstable. No matter how close I start to 0, I will always move away, and this one is asymptotically stable. So I see that it's the sign of f of x that determines whether I'm moving left or right and whether I'm stable or unstable. Now, looking at the graph of f of x here in the top right, consider this fixed point here at the origin. The sign of f of x nearby will be determined by the derivative of f of x at that point. In this example, the derivative of f is positive at x equals 0, which means that f will be positive when x is positive, meaning that that's an unstable fixed point. So we can make that idea more precise by looking at the Taylor series of the function. So let's take a a fixed point. So let's say f of x hat is equal to 0. And if I expand x nearby, that will be f of x hat plus x minus x hat f prime of x hat plus a half x minus x hat squared f double prime of x hat. And I could go on as many terms as I wanted, but I can simplify this because f of x hat is 0. So if I introduce a new variable u, which will be x minus x hat, to measure my distance from the fixed point, then du dt would be dx dt minus dx hat dt, but x hat is just a constant. So that is f of x. And using my Taylor series there, I get u times f prime of x hat plus a half u squared f double prime of x hat plus dot dot dot. Now consider the case when u is small, because I'm starting close to my fixed point. So that means the absolute value of u is much less than 1. Then the second term here, u squared, and all the higher terms, u cubed, u fourth, and so on, they'll be very, very small indeed. So when u is small, the most important term is going to be the first one. So I get an approximation du dt is equal to some constant a times u, where the constant a is just the derivative at the fixed point, which means the solution is going to be e to the at u naught. So we see that this, again, which is consistent with what we said on the previous page, if prime is positive, if a is positive, then u will increase and move away, you'll be unstable. If prime is negative, u of t will tend to 0. So my conclusion is, if the derivative at the fixed point is positive, x hat is unstable. If the derivative at the fixed point is negative, the fixed point is stable. And what about if the derivative is 0? Well, if the derivative at the fixed point is 0, unfortunately this idea doesn't work, because now I'm onto the second term. So from this method I get no conclusion. I'd have to actually need to work out the actual sign of f of x to determine the stability. Well, you might be thinking, why did I need to go to the trouble of the Taylor series? Why couldn't I just do that graphical method that I did on the previous page? The graphical method only works for scalar systems, so one-dimensional systems of differential equations. We want a method that will work more generally for larger systems, and the Taylor series method does work, as we'll see in a second. Let's just try out, we'll finish today by trying out this system. It looks like a rather complicated formula. Maybe I don't want to graph that function. It's also got two parameters in it, big K and little k. So first find the fixed points. So I said minus kx log of x over k equal to 0. Well, that means either kx is 0, but that's ruled out because x has to be positive, or the log of x on k is equal to 0. Well, that means I can only have the second one equal to 0. That means x over k is equal to 1. That means x is equal to big K. So there's one fixed point. I could call that x hat if I like. Now I need to differentiate f of x. This will be equal to, I'll use the product rule for these two terms. It'll be the first term times the derivative of the second term. The derivative of log x over k is 1 over x over k times the derivative of the argument, which is 1 over k, plus the derivative of the first term, which is minus little k, times the second term. Now that looks a little bit ugly. I want to simplify it. The k's will cancel, doing some algebraic simplification. Now I've got 1 over x in this term, the x's will cancel, and I get minus k log x over k. Now my fixed point was k, so we get minus little k minus k log 1. Log of 1 is 0, which is minus k, which is less than 0 because I was told that little k was a positive constant. Therefore the fixed point at k is a stable fixed point. Now if you had more fixed points, if the system only had one, then you'd have to check f prime, the derivative, at all of them and classify them separately as whether they were stable or unstable.